Thank you very much. Hi, Joe. That's a very strange way of communicating. I'm going to talk about this present work of myself, Ehud and myself, about interpersonal independence of knowledge and belief. During this presentation, of course, I'll refer to several works of Joe. It seems almost impossible not to refer in such a work to work done by Joe alone or others. But I must say that I cannot testify about the history of Joe's career. I wasn't there, but we cooperated in some projects and on some papers, and it was great. And what is maybe more important, not more important, but alongside with being such a good scientist, Joe is mostly a mensch, as they say in Latin, and a gentleman. And that's a great virtue. Okay, let's talk about interpersonal independence. So the question I'm raising here, we are raising here is this. Is there a formula F which describes agent one's knowledge, and a formula G that describes two's knowledge, such that the following holds, where F here, it means that F is logically equivalent to G. By the way, if you have questions, please don't wait to the end and interrupt if you can. So this is the question. And first of all, we have to say, what do we mean by a description of one's knowledge? That's simple. Here's an example of such a description. One doesn't know A, and one knows that either C or 2 knows B. Okay, so it's formulas that start with one's knowledge, and they are connected with connectors, logical connectors, negation, conjunction, etc. So the answer is, of course, what? Of course, yes. For example, if F and G are theorems or contradictions, then they are equivalent. So if F says, for example, one does know A or doesn't know A, then this is a theorem, it's a tautology, and it's equivalent to the same thing if I describe G's knowledge. So we have to exclude theorems and contradictions. So we do it, we require that the descriptions we are talking about are non-trivial, meaning they are not theorems, not contradictions. If indeed the answer is no, there are no such F and G, we will say that knowledge is interpersonal independent. So across persona, 1 and 2, agents 1 and 2, knowledge is independent. We're talking about S5 knowledge, by the way, which is the strongest notion of knowledge, but used mostly, almost exclusively in all written applications. The same question now applies. It's exactly the same what you have on the top. The question, the only difference is now the question is not about knowledge, but rather about belief. And if the answer, so the belief we're talking about is KD45 belief, which is exactly as knowledge, except that the truth axiom doesn't hold. So when one knows something, this something must be true. And when one believes, there is no requirement on the truth of what one believes. If indeed there are no F and G such that they are logically equivalent, then we say that belief is interpersonal independent. So, well, I think it seems obvious that, of course, there should be interpersonal independence for knowledge and belief, because what happens in one mind is unrelated to what happens in another mind. But let's see why this is not the case. Okay, so now I change F logically equivalent to G to F illogically implies G. Okay, so the same question, instead of logical equivalence, logical implication. And if the answer is no, then we'll say that knowledge is strongly interpersonal independent. Not only that F cannot be equivalent to G, it cannot even imply G, and a fortiori not be equivalent. The same question goes for belief. F logically implies G. And if the answer is no, we'll say that belief is strongly interpersonally independent. And here we see that it seems to be almost the same question, except a little bit stronger. And the answer here is for knowledge, yes, there are F and G such that they describe one's knowledge and two knowledges respectively. And F logically implies G. Here is the examples are trivia. For example, if F is one knows P, let's say that is a atomic formula, then obviously it's non-trivial, it can be true or false. And this implies immediately, since when one knows P, P must be true, it implies that two cannot know not P. So let's call it G, and we see that F implies G. Here's even a more trivial example. If one knows that two knows P, then two knows P. So you see that the knowledge of one implies knowledge of P. How about belief? Well, here, these two examples show the importance of the truth axiom. And the truth axiom does not apply in the case of belief. So indeed, in belief, we can show that belief is strongly interpersonal independent as opposed to knowledge. So let's summarize it. We have two conditions: strong interpersonal independence and interpersonal independence. And we're talking about knowledge and belief. And knowledge is not strongly, doesn't have this property of strong interpersonal independence because of the truth axiom. Belief, as we will show, does have this property. Therefore, belief has the property of interpersonal independence because it's a weaker condition. And the question is whether knowledge, what is the power of truth? Is it powerful enough to guarantee that knowledge also doesn't have interpersonal independence? That is, there might be F and G such that one describes one knowledge, G describes two's knowledge, and they are logically equivalent. So that's the question we are going to ask. So let's start with strong interpersonal independence. And easy to show that the problem boils down to the following question, or to the following theory. If B1A and B2B are consistent, then the conjunction of these two statements is also consistent. That is, any two beliefs of 1 and 2 are consistent, and any two consistent beliefs of 1 and 2 are consistent. Here is a proof. It's not really a proof, but it explains why we could know in advance that why the theorem is true. And here's how it goes. So we start with Joe's paper on the relationship between knowledge and belief and certainty that became later a whole book. This is a novelty because until, I would say, mid-80s, probability was used in modern logic only as a semantic tool, as an extension of the notion of truth. But this couldn't help to analyze beliefs about beliefs. And the idea, we are talking about probabilistic beliefs. And probabilistic beliefs appears as part of the objective language only, I think, by the this paper at least is one of the first papers that did it. Now, what Joe shows there is that in the finite model of probabilistic beliefs, the certainty part of this model is a KD45 model. Okay? So certainty part is assigning probability 1 to events, and this is a KD45 model. Okay, let's add to it a previous result by Mertens and Zamir that constructed a canonical model of probabilistic beliefs, and which turns out to be a product of the individual type spaces. What is a type? A type of an agent is a hierarchy of her beliefs. Now, we are talking about hierarchy, not syntactical hierarchies or anything of the sort, but about real hierarchies. That is, beliefs about some probabilistic beliefs about some parameters, and then probabilistic beliefs about the probabilistic beliefs, and so on. So it turns out that the types of the players are independent, and you take a product, which means that any set of types of agent one is compatible with any type, consistent with any type of types of the other agent. So we can conclude, since B1A will be interpreted in such a model, in such a canonical model, as the union of type of one, then of course, and similarly for B2B, then of course they will be consistent. It's a proof with quotation marks because it's first of all, it's too complicated to be the case. I mean, we're trying to prove something rather simple, and secondly, we have here a problem that all these results depend on a heavy structure of the model. Because you have probabilities over probabilities, you need a topology or at least a measurable structure. And it doesn't seem that the theorem on the top of the page requires any such a model. In any case, that's not a direct proof of this theorem. I don't know how to make such a thing a proof. And on top of it, the proof of the construction of the canonical model is anything but simple. So here is a real proof. Take a model, B1A is consistent. So there is a model in which B1A is true. Let's say that's the red oval. Here is what B1A is true. It must contain a set of worlds that are accessible from each other. So it's a full graph. Maybe there are several such sets inside. And the rest of the worlds in B1A go access only such states. And since B2B is also consistent, there is another state space. And all we need to do is just to add another world. And this world will be accessible exactly to the worlds in the black circle, to each one of them. These are the only things that it could access. The same way it happens here in omega 2. So the set of possible worlds will be omega 1 union omega 2 and omega. And in omega, B1A and B2B is going to be true, so it's consistent. So the proof is very simple. I won't be surprised if somebody already has done it before, I don't know. Okay. So here we are again, and now the question is, so this proof, of course, cannot work for knowledge because knowledge doesn't have strong interpersonal independence, and the question is whether it has interpersonal independence without a strong. And the answer is yes. And I'm going to show you the proof and discuss it. Okay. Interpersonal independence of knowledge, which does exist. Here's the theorem. There are no non-trivial formulas, F and G, which describe the knowledge of 1 and 2 respectively, such that they are logically equivalent. Turns out that for this, we need to use common knowledge. Okay, so we are not surprised that common knowledge surface again in this conference. And so let me define common knowledge in a way that hasn't been defined before, that is in these docs. And we'll do it in models and frames. Okay, so omega is a set of possible worlds, and pi I omega is the set of possible worlds that are accessible to agent I from omega. The knowledge operator will be defined on all subsets of omega. So it's an operator that goes from 2 omega to 2 to omega. And it satisfies the following property. Ki of an event, a subset of omega E, is the set of all worlds omega, such that the worlds accessible from omega by I are subsets of subset of E. Okay. That's really what you use when you take such a model as a model of the language. You really use KIE implicitly or explicitly. Okay, now we take the transitive closure of the individual accessibility relations. It turns out that this is an equivalence relation, and therefore it defines knowledge, and this knowledge is called common knowledge. Okay, this definition is very much, it's very close to the definition given in Aumann, Aumann's agreeing to disagree to common knowledge. And he hardly wastes time on explaining what the relation between this definition and the iterative definition. The truth of the matter that this definition is, it looks very formal, but it's very simple. And it's very intuitive, not simple. And it's the only definition of common knowledge that use the word common seriously and not metaphorically. What is common when you take iteration of all node, everybody knows that everybody knows what is common there. Okay, here it's common in the following sense. Imagine an agent, we'll call him the common knowledge agent, and this common knowledge agent will have an operator KC. What will be the property of the operator KC? It will be less knowledgeable than any of the individual operators. That is, anything known by KC is known also by the KIs, K1 and K2. But it will be the most informative one. That is, it will be more knowledgeable than any knowledge which is less knowledgeable than K1 and K2. Okay, that's exactly the definition given by Aumann formally, but it's very meaningful. It means that the common knowledge knows exactly what is known commonly by 1 and 2. Okay. Here is a theorem that is equivalent to the theorem on the top. So all theorems are equivalent, but it means that you can show that each one implies trivially the other. And here is the theorem. For each non-trivial f, non-trivial, that is not a theorem and not a contradiction, there exists a model in which KCF is different from f. So f brackets is the meaning of f. It's the event that corresponds to f in the model. And there is, so if f is not trivial, there must be a model in which f is not the same as kc of f. That's the theorem. Okay, let's say something about it, and let's bring it to the top and see what is the implication, or almost what the theorem says. The theorem says that it is impossible to define syntactically, that is in the language, a common knowledge operator KC. So be careful. The KC on the top is in the model. Now I'm talking about an operator KC in the language. So the question is whether we can write a formula that will say KC of F if and only if certain properties of F with other operator, with knowledge operator K1 and K2 will appear. So when can we have a formula that defines common knowledge in terms of the knowledge operators of the agents? Well, it seems quite obvious that it's impossible, but the question is, why is it impossible? How can you prove it? It's impossible. Okay, here comes Joe again. This time in a paper with me, with Ella Segev, a student of mine, and me. And another paper in the same issue. So the first one deals with the question of defining one modality with other modality. This corresponds to a similar question asked by Bell in first order logics. And the other one applies and further investigate the question of defining knowledge in terms of belief, an issue which bothers philosophers for a long time. There is a theory of justified true belief. So we examine this problem. So let me tell you what one of the observations of these papers is. It turns out that it is impossible to define syntactically an operator. So you start with a logic that has belief, one agent belief, and you ask, is it possible to write a definition of knowledge in terms of belief? And of course, you want the knowledge, not just knowledge, you want knowledge that is related to belief in the standard way. That is, when one knows, one believes, and when one believes, one knows that one believes. Okay, so so it turns out that it's impossible. You cannot write such a formula that defines S5 knowledge in terms of K before 5 belief operator. On the other hand, Okay, so summarizing, S5 knowledge is not syntactically reducible. There is a fine distinction between reducible and definable, but let's not talk about it. So it's impossible to define syntactically reducible to reduce S5 knowledge to KD45 belief. On the other hand, each KD45 belief model can be extended in a unique way to an S5 knowledge. So you start with a KD5 model, and you introduce immediately in a unique way a knowledge that that talks nicely with belief. So in other words, S5 knowledge is semantically reducible to KD45 belief. How come? What is the reason for the gap between the syntax and the semantics? So I'm going to add here one word. Look at this, not. So the answer is that indeed it is not semantically reducible. And the question is, how come? We just showed that it is possible to reduce it. And the answer is that you should look at wider semantics than Kripke models, and that is algebraic semantics, or without loss of generality, you have states of the world, but you have a knowledge operator that operates not on every subset, but on an algebra of events. When you consider such wider semantics, it turns out that indeed you cannot define knowledge on every model where you have belief. So the Kripke models have certain specific properties that are not reflected, that are special to these models and are not reflected in the logic these models serve. If you want to answer such questions of reducibility and definability, you should look at wider semantics that don't have these special properties of the Kripke semantics. Okay, let's prove it. A model is connected. We said that the model is connected if there is only one member of the partition of the common knowledge operator, and that's omega, of course. Or in other words, the relationship, the closure or the transitive closure of the accessibility relations covers everything. Every world connects to every other one. Let's introduce a metric. Arriving from omega to omega prime through transitive closure of the accessibility relations looks like this. You start with omega and you want to arrive at omega prime. So you go to another state, let's say by accessibility relation of I, and then you go to another world, let's say with J can be I, and then you go on and on until you reach omega prime. The metric will be defined as the minimal number, the distance between omega and omega prime is the minimal number of steps required to reach omega from omega prime from omega. Okay, since it's the minimum, this is really a real metric. Okay. Next, let me introduce a technique of gluing. It goes like this. You start with a set of worlds omega 1 and another one which is omega 2. You take an element of the partition in omega 2 and an element of the partition of the same agent in omega 1, and you simply unite. Okay, so you leave all the accessibility except in this set that we united. All accessibility relations are the same. If it's a model and not a frame, then you interpret every atomic sentence the same way. So that's a new model. Only of course it ruins everything because now the formulas that are true in omega 1 in each state omega 1 may now be completely different. So everything may change. But there is one nice property. If omega 1 and omega 2 are connected, then of course the glued model of omega 1 and omega 2 will be connected too. Next. Now, if F is consistent, then, so this is a claim now on the way of proving the theorem. If F is consistent, then there exists an arbitrarily big connected model in which F is true at some model. So here is the idea here is it's a cute idea. You start with omega 1 and a state omega where f is true because f is consistent, then it's true in some state of, in some world, in some model. Of course, we can take the model to be connected. There's no problem because, okay, simply take the connected element of the state omega in which this is true. Now, take an element of the partition which does not contain omega. Well, if omega 1 is too small, then there is a problem, but I'm skipping all the niceties. Now you take another space and call it omega 2. The problem that if we try to, we want to glue to omega 1 something else, and we'll get another bigger model. The problem is that if we just take any omega 2, then f will not be true anymore in omega. It will not be true. But if you take omega 2 to be a mirror image of omega 1, meaning that it's isomorphic, and the reason I call it mirror image because here I put it, and of course it will be connected because omega 1 is, and we take this element, bring it back, it's the image of the one on the left. So the element partition on the right is the corresponding one to the element on the left. So it looks like a mirror image. And now you glue the two models. And interestingly enough, f remains true at omega. So the truth value of formulas remains the same. So that's the trick, is taking a mirror image of omega 1. So you see now that we started with one model, and now we have another model which is connected in which f is true. And this model is much bigger. So we can increase it as much as we want. Second claim, the truth of f at omega depends only on the ball of radius depth f. Depth of f measure how many times one knowledge operator is in the scope of another one. Centered at omega. Okay, let's explain it. So you start with a model and omega, and you look at the ball centered at omega and with radius depth f, the depth of the formula f. Now, what this claim says that you can change everything out of this circle, out of this ball. You can change the interpretation of atomic formulas, you can change the accessibility relations, you can change everything as long as you keep all of them intact in the ball, and the truth of f at omega will not change. If f is true at omega, after the changes, it will be still true at omega. If not, if it will be false, then it will be false. So everything depends just on this ball. And here is the proof. Take a non-trivial f.
Dov,
Yes.
Can you start wrapping up?
Sure, yes.
Well, we're kind of out of time, so can you start wrapping up?
Sorry?
You're running out of time. Can you start wrapping up, please?
Ah, yes, okay. So we'll stop here. Okay, sorry.
Just say 2 sentences to conclude.
Okay. So the idea is very simple. I mean, you simply, if f is non-trivial, you take two models, one in which f is true, one in which not f is true, and you take them big enough and they are connected. Since they're big enough, what happens out of the ball doesn't matter, so you glue them, and now you have a model which is connected, and KCF is the empty set, because in a connected model, the only event that is that satisfy KCE equals E is omega, and since f is not omega because not f is true, and KCF is the empty set, and f is not the empty set because it's true in some state, and this proves the theorem. Okay. That's it.
Thank you. Thank you. Any quick question? Yes, madam.
Hi, thanks. That was interesting. I was just wondering, going back to the original question about interpersonal independence for knowledge, I would have thought like the route that you were going involved common knowledge, but I would have thought that the fact sort of rests on the fact that you can always find two partitions of a state space such that when you take any union of cells from the one partition, it's not equal to any union of cells from the other partition, except for the trivial union of empty or everything. I would have thought that sort of establishes interpersonal independence. Is that what goes wrong with that kind of argument?
Yeah, so common knowledge, as I've defined it, is defined on the model, right? And you're right. I mean, the question of independence boils down to the question whether you have events that are covered, paved with elements of the two partitions. Indeed, this is the definition of common knowledge. The point is that it's not clear that maybe there are F's and G's such that in all models are such. And then you have indeed the interpersonal dependence. And so the whole trick is to show that indeed there aren't any F and G, but it boils down to instead of F and G, you can take the F alone will suffice. There is no F that in all models is such an event. That is an event in the meet, or in the field generated by the meet. This is what you have to prove, and that's not clear. And may I add that the reason why it's not the case, because indeed, if you look at models that are not Kripke models, but rather algebraic models, then indeed you cannot define, and this is not well known, you cannot define common knowledge operator. So the idea that you have common knowledge operator is not a property of S5, it's a property of Kripke models.
Let's think Dov again.
Sorry? תודה לכם. Thank you.
Go ahead.